All right, let's talk about how we represent molecules. So there's a few different ways that we can represent molecules. The most common way is just what we call simply a chemical formula. And there's a few different variations on this that we're going to take a look at as we go through the next few slides here. But in general, what these chemical formulae do is they indicate the elements that are present and the number of them that are present. So for example, in water, everyone knows this, water is H2O. So we have two H's, which are hydrogen, and a single oxygen, whereas carbon dioxide is CO2. C is the carbon, O is the oxygen. So we have one carbon, two oxygens. Because in general here, well, not in general, but always, if you're not given a subscript, then it's understood to be just one, which we talked about on an earlier slide as well. All right, so these are the three most common types of structural or chemical formulas. There are empirical formulas, molecular formulas, and structural formulas. Now, empirical formulas, I'm not a big fan of. They have their place, they're useful in certain situations, but in general, they're not very useful. So we're going to kind of skim over that one and ignore it from that point forward. Molecular formulas, which was the second one there, this is what we've been looking at up to this point, essentially. The molecules that we've seen to this point, those could be called molecular formulas. So NaCl, CCl4, it's just the elements and then the number. That's all you get in these types of formulas. They don't actually tell you how things are connected together, they just tell you what is in the molecule, what's there. Structural formulas, on the other hand, not only tell you what is present, but they also tell you how the things are connected together. So they tell you what atom is bonded to this other atom, and then what's bonded to past that point. Like it shows you how everything is connected together. So essentially, as we go from one type of structure to another, you're getting more and more information. So empirical formulas, which we'll see in just a second, they give you very, very little information. Molecular formula give you a little bit more information, and structural formulas give you even more information. So it really depends on how much information you need. You might be perfectly fine just using the molecular formula, but there are some situations where you do actually need to know how the atoms are connected together. For our purposes, I would say 80% of the time or so, we're going to be just fine with the molecular formula. But there are going to be some situations where we do actually need to know how things are connected together. And so when we need that, I will give you the structural formula. We have some examples here of two different molecules. And what I'd like you to do is pause the video at this point and see if you can answer the questions here. And so both of the questions are the same for the two different molecules. And what you're doing is you're trying to figure out how many of each individual atom exists in those molecules, and then the total number of atoms. So go ahead and pause the video and try to work that out on your own, and then we'll come back and I'll work it out with you. Okay, hopefully you paused that and tried to work it out yourself. So the first one here is magnesium nitrate is what this is called, although the name isn't really important for what we're doing here. So we have magnesium, we have nitrogen, and we have oxygen in this molecule. We only have one magnesium. We actually have two nitrogens, because one thing we have not seen yet are these parentheses here. And what the parentheses are telling us is that this is a group of atoms that stays together. This is what we call a polyatomic ion. And beyond that, because there's a subscript outside of those parentheses, this subscript is applying to everything inside the parentheses. So we actually have 2 nitrogens, because each nitrate has 1, and we have 2 nitrates, and we have 6 oxygens. Each nitrate has 3, and we have 2 of them. So we have 1, 2, and 6, which gives us 9 atoms total. Okay, so then for the second one here, we have aluminum, which we have 2, because we have Al2. It's not inside the parentheses, so the 3 does not apply to it. We have 3 sulfurs, and we have 12 oxygens. And so total, we have 17 atoms. All right. So moving on here, there are a few other ways that molecules are represented. So we could use molecular models, like the ball and stick model as an example here. This is where the atoms are represented as little color-coded balls. So the color coding is shown here on the right. So the most common ones are hydrogen is white, carbon is black, nitrogen is blue, and oxygen is red. These other 4, mainly the chlorine does show up from time to time, but these 4 are the big ones that you'll see most often. And this is pretty common, especially in books. Now obviously if you're drawing a molecule by hand, it's not really practical to use the ball and stick model. But if you're reading something in a book, it's pretty common to see the ball and stick model. The other way to represent molecules is using what's called a space-filling model. And so space-filling models are actually the most real-to-life way of representing a molecule. So it shows the atoms not as little balls attached to sticks. So those sticks here in the ball and stick model, that is actually the bond that exists between those 2 atoms. The space-filling model is actually more true to life in that that's what a molecule would actually look like, other than being colorized, obviously. But if you could shrink yourself down and look at molecules, they would just kind of be these big blobs that are attached to other blobs. And so the space-filling model is actually the most accurate way of representing it, but it's not my favorite way because it can be hard to tell what's going on in space-filling models, because it is just kind of blobs stuck on other blobs. Especially in larger molecules, the structure kind of gets lost in the image. And so I do prefer ball and stick models to space-filling, and I think most people do as well, because it's fairly rare to see a space-filling model. Most of the time it is ball and stick. Okay, and so then here, just to summarize the differences here, we have molecular formulas give you the thing that is the atoms that are present and how many of them there are. Structural formulas give you the way that the atoms are bonded together. Ball and stick models are pretty much the same as structural formulas, only they actually show spheres as the atoms instead of the symbols. And then the space-filling model is the most true-to-life form of the structure. Real quick here before we finish this video, I do want to point out empirical formulas here, because I did say I was going to just very briefly mention them. So what an empirical formula is it is essentially the least common denominator, if you want to think of it that way, of the molecule. It's the simplest possible structure for the molecule. So like C6H6, because both of those atoms can be divided by 6, the empirical formula is just CH, which is the exact same as acetylene. And these two are very, very different molecules. They are similar in some ways, in that like they're both flammable, but in most ways they are very, very different. And so a similar thing here with glucose. Everything here can be divided by 6, which gives us CH2O. Ammonia is small enough that the empirical formula is actually the same as the molecular formula. Most of the time, empirical formulas are only going to be useful if you're using an instrument called a mass spectrometer. So mass spectrometers will give you empirical formulas. They can't tell you the overall structure, but they essentially give you the ratios. And that's really all the empirical formula is. It's just the ratios between the base atoms, the atoms that make up the molecule. So empirical formula is not terribly useful, but at the very least, if you come across them in the future, you should have an inkling in the back of your mind of what an empirical formula is. All right, so we're going to call it there for this video. In the next one, we're going to talk about molecular compounds versus ionic compounds, and actually start writing some of these out and naming them. So I will see you in the next video.